if I could click the script. All right, so the thing is that you don't need any type of data in order to do artificial intelligence, right? The only time that you need data is if you don't understand the way the world works. If you knew how the world worked, you could create intelligent systems that would be representative of what we already know and could give predictions and prognostications of what it is that we're supposed to do next. You use data to try to give yourself some guidance. Now, the thing is that AI, and this is not meant to be readable at the moment, clearly it's not, right? AI has a long history. You know, AI itself is at least 80 years old, at least from a computational sense. Now, the thing is that the notion of artificial intelligence in medicine, if you could see this, you can probably see it better online, goes back to around the early 1970s, maybe a little earlier. And it starts all with this paper that Shortlift had published about expert systems in the use of the diagnosis of infections within the blood. Okay. Now, this was a paper that Ted developed to try to figure out, like, what would it take to get a computational system to assist a physician in making diagnoses either at point of care or at a point that is going to assist in the treatment of the patient in a relatively quick amount of time. This is like a great vision of what artificial intelligence could be, right? And so this is, think about it, this is 50 years ago at this time. It's like, well, what happened, right? So it took until about 2019 for the federal government, for the NIH, to put together a committee, I guess it was 2018, to put together a committee that was going to look at specifically what were our needs with respect to AI and the sponsorship of biomedical research. Now, this is not to say that artificial intelligence completely languished for about 50 years. It's just that the entire concept as like a field and something that was really going to drive biomedicine, it took a little time to germinate. Now, what was notable about this was that they published their report a couple years ago. In this report, there were a bunch of recommendations. And these recommendations covered everything from make investments in infrastructure to come up with the ethical principles for what it would take to put AI out into practice, both for research as well as for clinical application. So I'm prefacing this with AI because, you know, when I was initially asked to come in, I was told, you know, it'd be great if you could talk about data science. And like the whole point of this is like the future of data science. But what you have to recognize is that data science itself is part of the bigger picture of AI. And yet at some point, it's not, right? So what you have to understand about data science is that it's this really interesting amalgamation of a bunch of different fields. And so I'm standing here and a lot of you look at this from the perspective of bioinformatics. Okay, but let's look at this in that it begins with knowledge. You have to have some type of knowledge, not necessarily data. Okay, you also have to have some mathematics and statistics at the table. And if you bring the two of those things together, what you're looking at is biostats. And then you bring the computational sciences in. And when you bring the computational sciences in, you have the opportunity to define bioinformatics or biomedical informatics, which is where I live, or you have the ability to define machine learning, which was at the center of computer science and mathematics. Now, that is squarely where AI ends up living. Okay, but data science sits at the intersection of all three of these, right? It's where the knowledge really comes to drive what it is that you're trying to learn. Otherwise, all you have is just foundational methodologies. But we know that those foundational methodologies can fail spectacularly if you don't understand the domain in which they're being applied in. Okay, so data science itself, again, like AI, it's not new. So back in the 1960s, John Takei, in the future of data analysis, really started coming up with the principles for what data science would be. And if you're not familiar with 2K, you really should take a look at like the history of statistics in this one. I'll talk more about this in a bit. But in this paper, he talks about a couple things. It's like, I really love the way that people wrote in the 1960s in scientific papers because it's completely different than the way we write today, right? So one of the things he said was, for a long time, I thought I was a statistician, interested in inferences from the particular to the general. He said, but as I've watched mathematical statistics evolve, I have had cause to wonder and doubt. I want to write papers like this, right? I have come to feel that my central interest is in data analysis, which is intrinsically an empirical science. And then he goes on and he says, how vital and how important is the rise of the stored program electronic computer? Okay. And what he went on to say was that the computer was going to be what drove everything we did, because Tukey believed in information visualization. And he said, if you can't get intuition directly from the stats itself, you may be able to get intuition from looking at the data. Okay. And that's where he saw this interplay between what it is for data to just be data versus this whole notion of human computer interaction and the ability to play with it. So let's fast forward to where we are now. Like, we're at the point where we're generating data at an obscene rate. This leads to a number of new challenges. And this has been in the big data communities, what they refer to as the big Vs. Okay, so what we're seeing is an increasing amount of volume of the data. We're going from terabytes to petabytes. We're easily starting to hit exabytes in certain areas, especially if you're in imaging. And the velocity at which this data is occurring is speeding up. Right? It's coming in at an ever faster rate, and we're always being asked to study the data as quickly as possible. Right? People want the data released from new studies almost instantaneously, and they want to be able to do a new study overnight. The variety and the heterogeneity of the data is also starting to change, right? And it's not just all about one type of data. There's multimodal data, and the data has ambiguities and there's inconsistencies associated with it that we need to have a way of wrangling and resolving as we're doing this. And then the veracity of the data comes into question, all right? Now, what I mean by veracity is, do you trust the data? There are errors that exist in the data. People, if you're collecting the data in terms of like electronic medical record systems, you have to wonder, is the patient telling you information that is trustworthy? Right? And that's not always the case. And then finally, I advocate for a fifth V, which is what I call value, in that you need to be able to demonstrate that the data that you've collected and that you're using has a benefit to the population that you're trying to apply it to. And if it doesn't have value, then you may be collecting the wrong data and you may be looking in the wrong space. So when you're talking about data science and when you're talking about machine learning more generally, there's this process that we really need to think through, because if you don't represent the process, you may end up working in an inefficient manner. So you collect your data and then you're going to subject it to some type of an analytic process. And a lot of what we do today in machine learning is, you can really think of it as a black box. I don't think anybody's really going into a deep net is going to hand manipulate any of the edges that connect any of the nodes. Does anybody do it? No? You're not alone, right? So you use this tool, right, that somebody's built, or you may have refined it yourself. And then what comes out of that tool is some type of a model, right? You look at this model and you say, does this gene interact with this gene? And does it have this influence on the outcome for a patient or for a research participant? And you say, does this make sense? Or are the confidence intervals something that I'm not completely comfortable with? And if it's not, you go back and you retrain, right? And you tune your system and you tune your model until you're comfortable with it. And if you're a graduate student, you keep doing this until you make your investigator happy, right? At the same time, you might say, I don't have enough data. And that's where you go to augment the system and you start looking around saying, do you have data? Do you have data? Or can I go about generating more data, right? This is an entire process. All of these are steps that if you address them appropriately, you can rapidly speed up the investigational environment. Now, where I'm coming from, so I live in a med school. I live in a medical center itself. And one of the places where we generate data is the electronic health record system, or the EMR, depending on how you want to look at it. Now, I really have to thank Bill Stead and Dan Macy's for this perspective, in that this is an environment that is an opportunity to serve as a living laboratory. Now, we don't want to do it, instantaneous experiments on patients in an uncontrolled manner. But as data scientists, we should have the opportunity to look at this as an environment where we can issue a query, pull information out of that environment, study the data, and then push knowledge back in a manner that's going to facilitate the care of the patients. But again, this is a process. But I'm arguing that this is an environment where you need to let the scientists be the scientists. So I'm going to give you a couple of ways in which I think data science has an opportunity to drive what we do as scientific investigators in the biomedical domain, and give you some illustrations of what we've been able to accomplish over the last couple decades and why we think this is the right way forward, or an opportunity. Okay, so principle one is that you need to figure out how to make data more accessible. And so one of the ways that we did this at Vanderbilt was that we took all the electronic medical records data, which sits in what I refer to as the operational environment. That's the hospital. And we said, one of the things that slows us down is when we ask for access to data to people who are managing these systems and making sure that the patients are receiving care. When we ask for that data, the response that we get is, we'll get to that in a couple days. It's like, that's not fast enough. So what we did was we created a pipeline, and it took a while to get the administration on board for doing this. But in addition to just siphoning off all of the data that was being generated in the system, we figured out that we needed to standardize it, make it more easy for people to work with. And so we partitioned all the data into different types. And then we had a whole set of standardization processes associated with these, with the notes, with the clinical orders, with messages that took place, the labs. And so this is just all sitting in a research environment that's outside of the control of the operational setting. So right now, we've created this environment that, it's around 2.5 million medical records, and it just sits on a computational environment that we make accessible for research. Okay, so that's step one. Now step two, so once you make that data accessible, you need to make analysis fast. And so one of the ways in which we did this is that we licensed initially this little supercomputer in a box. All right, so this is a Netezza twin fin. And at first I didn't want it. And then I'm working with people in the Med Center, and I saw an illustration of this thing, which this is a warehousing appliance that the way that it was designed, and we got to work with the group on this a bit, is that it's a bunch of blade servers that are all rated together. And then we put FPGA chips on top of them. And the FPGAs allow you to dynamically compress and uncompress the data such that you can do queries at scale efficiently. What this allowed us to do was we didn't have to index medical records anymore to query them. We took all of the data and we dropped it into 64 KB blobs, to the point where if you were going to query the data, you would get an answer back across a search over all of the free text on 2.5 million records in about a half a second. I was demonstrating this to one of my summer undergrads a couple of days before I got out here, and they were just like, oh, this is amazing. One of the reasons why we did this was that when we made the data accessible to researchers and we said, okay, issue your queries, see what you can pull out of the data, you would issue the query. We had all the data loaded on the Oracle databases such that it was load balanced across like 50 databases. Query would run, people would wait for about 5 minutes to get an answer. They go off, they get a cup of coffee, and they look at the answer and go, that's not exactly what I want. And then they'd issue another query, and they do all this again. Okay, when we made the data accessible, this was in 2007, we had about 10 people who were power users of the system, and they were interested in doing this, and they were willing to do this over time. When we moved it over to the supercomputing type of environment, we ended up ramping up the number of people who were interested in it because you could do interactive query response. You were able to address your queries in a refined manner. You could do this over time with almost instantaneous results. You made the data playable. And so we moved from about 10 users to about 1,000 users over the course of a 3-month period. The other thing that we did was that we took the time to build research pipelines. And if you're in genomics or in your proteomics, I think you're familiar with the principle of just figuring out how do you create a process of taking the data, moving it through the analytic infrastructure, and then building it out into some type of a visualization so that you don't have to rewrite your code over and over and over again. So the Paramo system was a project that I worked on with some friends over at IBM to try to figure out how do we speed up queries over electronic medical record systems and how do we build machine learned models on top of this. One of the things that we did along the way was that, and you're not meant to be able to read this, this is just a dependency graph. What we found was that a lot of the statistics that we were interested in computing, they drew upon the same foundational raw counts and intermediate statistics that were going to be useful over and over again. And so we just said, let's compute that once, so that we only have to have this process, we can optimize this process. And so we ended up speeding up the creation of a machine learning model from going from like about 10 to 20 minutes, and we brought it down on average to about 20 seconds. Okay, so this is all about making things faster, making things more accessible. Then the question becomes cost, because what I just explained to you was we spent millions of dollars in investment in infrastructure that worked at Vanderbilt. But in reality, what a lot of people are doing is they're rushing out to the cloud, and they're going out to Google Cloud Platform, or they're going out to AWS, and they're saying, I don't have to have my own servers. The public cloud is already out there. A lot of the toolboxes that I'm interested in working with sit out there. So why not move out into the cloud? Okay. So here's a day of introduction to the day of somebody who works in the cloud. So you got your data, you subject it to your analytic infrastructure sitting on the cloud, you run it once, you spend, a decent amount of money. And the first time you run it, what happens? You get junk, right? The first time you run this, I guarantee the answer that you're looking for is not going to be there. This is almost always the case when somebody runs a machine learning framework. All right. So what happens next? Seeing if anyone wants to shout it. No. You pay more money and you run it again, right? You tweak some things, you get a little bit more data, and you run it again, right? And then what happens? Out comes something that looks a little less junky, right? It's like, okay, I'm moving in the right direction. Okay, so I say this out of like experience with some of my grad students and postdocs who have burned through thousands to tens of thousands of dollars trying to build their machine learning frameworks out in this domain, right? So next step. I can try. Yeah, there we go. Okay, so you throw lots and lots and lots of money at this, and eventually you get to the point where you do something so amazingly wonderful, you get a Nobel Prize, right? I jest in this, but this is the principle that what ends up happening is that right now, when you move everything out to the cloud for biomedical research infrastructure, it is not cost effective, and this is just like a poor allocation of funds. This is still an open problem, though. I don't have a solution to this. What I'm actually advocating for, and this is why I say there's a promise associated with biomedical data science, is that we need to figure out what's the right type of a hybrid strategy. And so this is what we started working on in our group, where you do some things local, you do a lot of model tinkering local on your own servers, and then when you're ready to run it at scale, you move it out into the cloud. But how exactly that gets managed, that's not really solved yet. Okay, so the next thing that you need to work through, or that an illustration of what we've worked through, is this notion of regulatory frictions. And I get this question a lot. It's like, okay, well, that's really amazing that Vanderbilt could build up that infrastructure, but how do you speed up the time to access the data that's going through the IRB? And so what we did was that we took the IRB out of the equation. And we ended up, we generated a completely de-identified, I say completely de-identified, de-identified is a legal term, but we de-identified all the medical record system. And therefore, whenever somebody wanted to gain access to this, we said, we've already gone through the entire process of getting a non-human subjects designation, and therefore you don't have to make an application and wait months for access anymore. Now, this was done, we created what was called the synthetic derivative on top of our research derivative. And then we extended the synthetic derivative to include biospecimens. And I could spend a very long time explaining like the entire process for biospecimen collection, but this was done in the context of clinical care. This was leftover blood specimens that we had consent for using in coordination with the medical records for research purposes. And so we just, in this situation, it's a consistent hashing process so that we've got a consistent way of updating these records over time. And this is an environment that we've been generating for the last 15 years. What's notable about this is, remember I said there's a process. You can't see exactly what it says up at the top, but this process, though we started the creation of this resource back in 2007, it went back several years before that. And we really wanted to make sure that we were engaged with our community so that we weren't using data in a manner that was considered to be inconsistent with their expectations. And so there were a whole series of focus groups and patient surveys, and we ended up running newspaper stories out in like the Tennessean, which was our major newspaper, just so that people were aware of what was going on. We said, this is going to happen. We're going to start collecting your specimens and combining it with your medical records for research purposes. And so we went through all these steps to get there. And then when we went and we got approval, we told everybody we're going live. And we didn't go live. We did a 6-month test run where we said, here's a phone number for somebody that you can call if you have a concern with what we're doing. We got a couple phone calls. That phone number went directly to my department chair at the time. And the major argument was not from most of our patients. The argument was actually from faculty within the university who disagreed with doing research in general. It was a really long story on that. Cool. So we started. And once we made that data accessible, or we had the data and we're humming, we created a 2-tier access model. The first one was for initial hypothesis generation, because not everybody wants to see the data all the time. So we created an interface. It looks a lot like I2B2 if you're familiar with it. And people can issue, what you see is what you get, queries, and then we give them back aggregate results. There was no oversight associated with this whatsoever. The second step was, once you have an intuition of what you want to do next, is that you come to us and you enter into a use agreement. And this is where we say, we're going to give you individual level records, but we also don't want you sharing all this information with the rest of the world. There's not complete accessibility at this point. So that's the point at which we give out the individual level records and people are able to start doing research with it. We did not set up the infrastructure at that time that allowed people to run any type of the analytics on our own servers. So at that point, there was still this separation that said you still need to have a computing environment on hand to do this analysis. And that was because everybody wanted more flexibility. Couple things that we did along the way that I think are notable. One was that we created a natural language processing environment for doing de-identification of the clinical notes. Initially, we worked with a spinoff from UPMC, which was called DID, and we ended up wrapping their technology with some pre-processing and post-processing strategies. And I'm saying here that we did some tests where we showed that we tuned the system so that it was hypersensitive, so that we could get recall on patient identifiers that was like almost at 100%, but you could never completely guarantee it. That was based on a lot of rules. It was a huge dictionary and regular expression-based system. And I was really concerned that we were spending way too much money on this. And so we then looked at what could we do from a machine learning perspective, and we started playing around with pick your favorite machine learning methodology. We ended up really focusing on conditional random fields to make this scalable and reusable at other institutions. And so the methods that we developed ended up getting adopted into a couple of different technologies out there. One was called HYDE from Li Xiong's group in Emory. And then another one is the one that has kind of become the standard, which is what's called MIST that John Aberdeen developed with us. And then more recently, I've been doing a lot of work at the Mayo Clinic and with a new company that's called Inference. And we developed an ensemble-based learner approach that's based on transformers like BERT. And so this is a technology that has become way more scalable, way more reusable. But the way that initially was designed was that it had this redaction problem. And so redaction's good. You want to get rid of the identifiers, but you run into this residual problem. Like I showed you before, the recall was 0.999. But that means that every once in a while, you might have a name pass through. And so we were like, well, that's not really a good thing. And so that forces you into a situation in which you go, well, there's an unknown level of risk associated with this. Like it might say like the senator's wife, or it might say like, the name of a child. And so we said, look, this is why the use agreements are in place at this point. But we said, could we push this further? And so we were like, okay, one of the things that you could do, and seemed to make sense, was that for all that residual information, what if you took all the redacted data and then you replaced it with fake information that looked like the real data? And so this turns into what we call like a text-based steganography solution, or it's hiding in plain sight. And we're like, okay, well, it looks good, but let's bring this in front of humans and let's ask them if they can tell the difference. So a lot of numbers here. Short version of the story is that the humans get really confused. Okay, they're just not good at telling the difference. all I'm saying here is that what that meant was that effectively raised the de-identification performance to a level that we felt extremely comfortable in sharing this information. I'm now working on the institution to try to allow some of this data to go out into the public domain. But it runs into what's called a Parrot problem if you're not careful. And this is where I wanted to show you, like, this is one of the ways in which machine learning goes boink. So the Parrot problem goes as follows. Let me just make sure we are on time here. Parrot problem goes as follows. I use machine learning to learn a pattern to detect where all of the identifiers are using the real data, okay? Annotate the data, find the things that you've annotated. Now, there's going to be some things that are residual, so let's throw all of the fake data into where the real data was. All right, let's throw that data across the pond, let somebody else look at it. Now, here's the challenge. If that person assumes that I've done really well in doing the de-identification, then what they can say is, I'm going to annotate all of the identifiers that I see in your data as fake information, even though some of it is not real, even though some of it is not fake. And I'm going to go train my own model using the fake information. Now, at that point, that parroting or that mimicking of what we've done is going to allow them to learn the model that I used to find the identifiers. And so when they detect fake information and pull it out, the only thing that's remaining was the real stuff that I failed to get the first time around. So this is a dangerous precedent to set. So it looked really good, but the Parrot problem was real. And so we said, okay, so why does this happen? This happens because machine learning migrates towards finding patterns that are representative of the system at a large. So we said, okay, let's change the way we do training. And so we introduced a new strategy for machine learning, which said, let's do training once, and then let's hold out all the things that we were good at getting the first time around. And then let's retrain the system with a focus on all the things that were considered to be difficult the first time around. Now let's make that a second model, all right? So do the initial training, let's look at all of our false positives and retrain again. And then let's pull all those out and let's focus on the things that were really hard again. And then let's do that one more time, or like, let's just keep doing this until we can't learn a better model anymore. And so this is what you call an iterative scalable learning framework. This was a strategy that we showed that when you do this with medical records data, and we did this with a public data set from the I2B2 program, we showed that it required about 4 steps in order to get to a point where you had a much more high fidelity system, such that when somebody tried to parrot us, they could do no better than random. We felt really good about this. We felt really smart. So we said, okay, cool. So now we know that if we're going to do privacy, if we're going to do something at a level that we feel comfortable with, that we're not really going to be attacked down, what could we do to show the value of this data? Because it's one thing to create the resource, but until I get to go back to the CEO of my medical center and say, there's a reason why you're investing $1 million in us, or millions of dollars in us. Like, let me give you some idea of what the return on investment looks like. So I'm going to walk you through what a couple of the people in my center are doing with the data. So Tom Lasko, oh, nothing shows up here. Wow, you can't see it. Okay, so this is a visual. So Tom, here you go. What you would see are like lines. In this situation, you'd see uric acid patterns over time. What Tom did was that he developed basically the first deep learning approach using Gaussian processes to show that you could come up with different types of trends, and that you could see that there were different phenotypes of patients that existed in the system, some who were more responsive than others to various types of care. So they're learning new types of phenotypes on this data, clinical phenotypes. And they're allowing for more richer representations. So you get better correlation with outcomes. More recently, what they've been working on is that they can show that by looking at the lab data, you can get predictions of breast cancer at an order of around 3 to 4 years earlier than when the diagnosis shows up in the medical record. That doesn't mean that we didn't know that they had cancer. It just means that the diagnosis wasn't there. With the natural language data, Jejun Yin's group is trying to understand what the semantics are and what the sentiment is that is expressed by patients when having a discussion with their providers. So it's like, why would you care about the sentiment at that point? So one of the things that he was really interested in was you put somebody on tamoxifen after subjecting them to a double mastectomy, and you say, look, you need to stay on this for 5 years in order for this to really have some type of an effect, and preferably for 10 years. But when you listen to what the patients say, you learn all of these things about why they're having trouble staying on the regimen. Some of it is financial difficulties, some of it is an artifact of side effects. And what Jejun ended up learning when working with a cognitive psychologist was that you can learn the different personality types of the patients, and you can see when individuals are going to be trending towards staying on the regimen versus when they're not. Is anybody familiar with like the 5 big factors of personality? Yeah. So if you use those, it turned out that there was like one huge driving factor to determine if patients were going to stay on their regimen, and that was narcissism. Not kidding you. So if you look at the way people talk, they were people who had fear of failure, and they did not want to present themselves to their family or to their friends as people who were quitters, and they were just very concerned with their own self-preservation. And we were just like, oh, that's really interesting. Now, we don't want to make all breast cancer patients narcissistic, not necessarily, right? But we do want to use that fact to say that we want to try to figure out how do we create systems that orient providers to recognize when patients aren't necessarily exhibiting symptoms of staying on track. Okay, so what's interesting about this was that we were only able to do this once we de-identified all the patient portal communications, because the electronic medical record system was mainly about documentation done by physicians and nurses, and it didn't take the patient's voice into account. So this was a whole project that led to a National Cancer Institute study, or an R1 that started a couple of years ago, to try to figure out how to expand this to other types of treatments. Another thing that you can do that might not be expected, right? I know that I'm talking about bioinformatics department, but let me give you some intuition of what you can do with healthcare administration. So Yo Chen's work, who I'm proud of because one of my former postdocs, showed that if you look at the way the organization interacts with the medical record system and thus is interacting with each other, then you can see organizational structures, and you can use that org structure to give some intuition into whether or not a patient is going to fare well in their management. And so what he showed through various types of social network analysis strategies was that you could find bottlenecks with respect to post-trauma management. And he was able to show that for some types of patients, if they hit like the right type of management structure, they'd be getting out of the hospital about a day or two earlier, which is substantial. I mean, and that's really impressive in terms of like the amount of time that you save, the amount of money that you save, and it reduces to a lower amount of morbidity for the patients. Okay, so that's just an illustration of what you can do with medical records data, both obvious and non-obvious. So now you want to get bigger and you want to get better. So these are demonstrations of what happens at Vanderbilt, but you really want to have safety in numbers. And so what do I mean by that? So we have this entire infrastructure that I talked about. This is a process for learning. And so now I want to look out and I want to come up to Michigan and I want to say, do you see what I see? Could you do the same studies locally that I've now done, right? And so I wanted to have a situation in which you're able to run exactly what we've done. You know, I would love to be able to create Dockerized environments where I just send this to you and say, give me your answer, right? The whole point of this is to generate robustness in the patterns that we learn. So how do you get there? So the way in which we started this was with the establishment of the Electronic Medical Records and Genomics Network. So this was an NHGRI sponsored program that started back in 2007. And it really was this consortium of everybody that kind of looked like us. And what we found, man, this just looks horrible, is that you would generate a phenotype. Like, so for instance, if you wanted to study patients with diabetes or type 2 diabetes in the EHR, you would develop it locally And then you take that phenotype strategy and then you throw it across the fence and you say, hey, use the same thing with your environment. Tell me what your recall and precision is with doing this. And then we learn what worked and what didn't work. You know, was this diagnosis code defined correctly for you? Do you use a different diagnosis code? We had like illustrations, for instance, where we'd find that at Vanderbilt, we would use a diagnosis of like irritable bowel syndrome, whereas up at Northwestern, they were saying Crohn's disease. And so we just had to have some type of a harmonization there. But this was an entire process, and we thought that we could automate it. Extremely difficult to automate right out of the gate. So what we ended up doing was we created a public resource that everybody could contribute to, and this became PhD, or the Phenotype Knowledge Base. And so PhD was everybody could throw up what their definition of a phenotype was, so that other people could see what was being done at other institutions, and then they could provide comments and feedback on what worked for them and what didn't. This is kind of like the baby steps towards trying to get coordination. More recently, this doesn't look that great. More recently, we got to the point where, remember I told you that the NIH was starting to get interested in AI. About a year ago, they issued this RFA for this new program called Bridge to AI, where they want new data sets that are going to be generated across different sites. And they're going to do this in a manner that's going to make the data publicly accessible and reusable. So this is a program that's supposed to start in about a month. And I would encourage you to keep track of what's going on here. There's some things I can't say publicly yet. Okay, so this is the notion of getting more data and getting more people involved. But then we also want new data types. All right, so I encourage you to get to broader data. So we've talked about DNA, we've talked about some things with socioeconomic status and medical records, and there's all types of clinical trials data, but what we're not seeing so much is all the other stuff that people want to use to try to understand what's the etiology of patient disease and management. So like, how do you get into like retail data? How do you integrate social media data, fitness records, get lifestyle information? And then how do you do this with respect to families? How do you do this with respect to like a parent and then what's going on with their children? So this is where the All of Us research program comes into play. Is anybody familiar with All of Us? Some of you. Okay. So All of Us was something that Francis Collins started, you know, about 7 years ago. It was signed into, like, we got a special designation from the White House to do this. Like, it was a special allocation. It did not come out of the NIH's budget. Basically, before Obama left office, he signed off on an allocation of around $1.2 billion. It's now grown to about $2 billion to say, we want to build a 1 million person cohort where it includes medical records, genomic data, as well as fitness information and patient reported outcomes. So we were interested in this because this sounded a lot like what we were already doing at Vanderbilt and in the eMERGE network. And so what, you can't see it here, but what we built it. So Vanderbilt ended up becoming the Data and Research Coordinating Center. Michigan was part of that. The center is actually distributed across Vanderbilt, Michigan, Northwestern, the Broad Institute, and University of Texas Health Sciences Center. The browser, let me see if I can I make this smaller? It just goes like this. Okay, so if you're not familiar with it, I strongly encourage you to go to our data browser. So this is going to show you all the data that we have in an aggregated fashion for all the participants. So at the present moment in time, we're at about 400,000 participants as we're growing. And so you can look from the EHR domain. What you can't see here is that as of last month, we just released the first batch of whole genome sequencing on everybody. It's 98,000 whole genome sequences, as well as the survey questionnaires that we've put together. This is just an illustration of the types of things that you'll find in there. And so what you see up here, even though you can't see it very well, is that this says 160,000 and this says pain. Okay. This is an example of, this is traumatic injury at right around 100,000. Now what we ended up doing was we created a researcher workbench. And this was where we partnered with Verily and the Broad Institute to take example, to reuse the Terra biosystem. And what the way that we architected this and the way it's currently running is that it's all sitting out on Google Cloud Platform. And then on top of GCP, we put all the data into a BigQuery environment. And then on top of BigQuery, you have Jupyter Notebooks that sits on top of it. And so when you come into the system, you can create your own virtualized Jupyter Notebooks environment and then start interacting with the data. And so it's available now. We're now up to about 1,000 users, and it's growing on a daily basis. As I was alluding to, this is a tiered level of access. So we have public data, the aggregate summary statistics, and then we created sandbox environments for everybody to work in. The first is what we revealed 2 years ago, which is what's called the registered tier, where you get access as long as you're a trusted organization and you enter into a data use agreement with us specifically. And we de-identified all that data to a low risk of re-identification. And then the controlled tier is what we just released 2 months ago, and that's where you get all of the genomes. I'm going to run out of time. I could spend a long time walking you through how de-identification works in this environment, but I'm not going to do that. What I do want to highlight is kind of like the future of data science and some of the things that need to be addressed. And specifically, I wanted to highlight this notion of data skew. And I refer to this as you get skew in, you get skew out. Some people refer to this as bias, but it's not bias, it's data skew. So an example of so when we do de-identification of that data to put it out the door, there are certain types of demographics that we need to hide in order to make sure that the data is not readily identifiable, particularly for small populations. And so what happens is so you don't have many transgender individuals, you hide the data. You don't have many Pacific Islanders, you hide the data. You don't have many people from rural settings, so you hide the data. So in other words, this notion of de-identification, it's only useful when you have data of a sufficient size. So what that means is that you have a privacy utility trade-off. And let me put this up. And so what ends up happening is that this is what it looks like for a majority population, which in the US has typically been, Caucasians. And however, when you shift over to minority populations, you end up with a much faster trade-off. And then with your super minority populations, your extremely small populations, it's an even faster trade-off. Now, this assumes everybody has an initial level of utility that's equivalent. But in reality, it's not quite like that. It's more like this, right? And this is the problem with equity. So when you say that there is a fixed privacy requirement that everybody needs to adhere to according to HIPAA or according to the common rule, that what ends up happening is that everybody ends up with a different level of utility at the end of the day. Okay. So this brings up the question of fairness, right? And a lot of people are now starting to look into fair algorithms and algorithmic bias. And so what we need to recognize and figure out how to solve is that when you amend minority data more than the majority data, you end up in a situation in which you get to learn more about the majority, which means you will make better policies for the majority population, and the rich, so to speak, get richer. So you have to ask this question of, should you apply an excessive amount of majority records? Should you amend more majority records in order to achieve balance? Or should we create policies that allow for a better trade-off between utility and privacy, so that we figure out that we say it's not just privacy that's driving whether or not data can go out the door, but societal value. So there's a push for diversity in this respect, and that's the future. All right, so I think that everybody recognizes this history, and that if you look at genetics research over the last 50 years, there's been a huge white bias. And so if you look at the studies that have been done, what we see up here is this is the number of individuals involved in studies. This is from a paper that we published with all of us about a year ago. That the majority of individuals that have been involved in these studies have been Caucasian. And the studies have not always been about Caucasians, but you still have over 50% focused on Caucasian populations. And the big drawback to this is that when you go to build risk predictors or when you go to build algorithms based on these populations, they don't generalize well to some of the minority populations. This is something that we've seen over and over again. So one of the things that we've done within all of us, and I'm here to encourage everybody to do this with all the other cohort studies that they're working on, is that we've made it our goal to ensure that we have more than 50% representation from groups that have been underrepresented in biomedical research over the last century. Now, that doesn't mean that we get to a point where the balance has completely tipped in that direction, because we're still in an active recruiting stage. But we're working to create a more diverse resource as a result. And so then this is also where the NIH, I think, has recognized that there's an opportunity. And so about 5 years ago, we had the big data to knowledge push towards enhancing diversity in biomedical data science. And this was their first batch of R25s. And then more recently, this call just ended. There was an R25 push to get more diversity in biomedical informatics and data science careers. And so there is an active investment that the NIH is starting to make, but these are only R25s. For those that are familiar, these are relatively short-term training environments. It's not the same as making major investments in huge training programs. So we've taken it upon ourselves to invest some of the money that we've received at all of us to create these types of training opportunities. And so we have created a minority student research symposium, and we started partnering with historically Black colleges and universities, as well as minority serving institutions, to try to show what you can do with the resource that we have, as well as highlight what we don't have the ability to do. I'll leave you with this part, just a couple of things. So one, the NIH did institute a new program last summer that I'm one of the PIs for, which is called AIM-AHEAD, which is the Artificial Intelligence and Machine Learning Consortium to Advance Health Equity and Researcher Diversity. Big mouthful, right? Which is why it's called AIM-AHEAD. And the whole goal of this is to create these relationships with HBCUs and MSIs to really get them involved more in the research process, so that we have more researchers, and not just data, but researchers who are trained from underrepresented groups. If you're interested in learning more about this, you can go to aimahead.net. And so we are going to be doing a summer symposium on health equity and AI that is going to be done at the end of this month. And so the details are up on that website. I think, I can talk, as I said to somebody before this presentation started, I can talk until the cows come home. I had a whole nother section prepared, but I think I'm going to pause there because I'd rather give you guys some time. And so I'll stop and I'll say thank you for inviting me to come to talk with you. It's been 2 years in the making. When Brian asked me to come out and give this talk, it was a couple months before the pandemic hit. And then I remember it was April of 2020, and he goes, we're gonna try and get this, to work out in May. And I was like, Brian, I don't think this is gonna happen. So it took 2 years, but I sincerely appreciate you allowing me to come and speak with you all. Thank you. And I know it took a little extra time, but if you have questions, I guess we should take them now. All right.
Thanks. Hey, Brad, wonderful talk. I just want to ask you a question about incentivization. Okay, I'm going to try. Exactly. So about incentivization, both from the researcher's perspective and the participant's perspective. For example, I've seen that a lot of the minority populations might think that what's the point of enrolling when it's not going to really help me? So how do you incentivize that branch? Second is, for the researchers, a lot of this is data cleaning, a lot of the stuff that nobody wants to really do. How do you incentivize that for the people who have ideas, but not the incentive structure to do it?
Okay, so let me take those one at a time. I'll take the easier one first. This is crazy. The easier one is the participant encouragement. So there's two components to this. One is that you really have to listen and you have to ask what they want out of the program. This was before all of us started. We did a roadshow of studios, not promotional, but we went around and worked with various not-for-profit organizations as well as patient representatives, and ask them, like, what type of research do you want to have done? What type of data do you want to have collected? At the same time, and so that allowed us to prioritize certain types of information over other types of information. One of the things that we learned was that it turned out privacy was not a big driving factor for a lot of participants. They really just said, are you going to use the data so that either I or people who are like me get benefit? And if you do that, we're on board with it. Now, that's not the only thing that you're supposed to do, but this notion of having empathy and recognizing that it's not just data, that it's people, and that you can somehow get back to them, that's critical. So we did not initially have plans on doing any return on results to participants. And after we ran the roadshow, we said, this is going to become a priority. And this was tricky because you're going to generate whole genome sequencing data on people and you're going to give it back to them. And and so we said, okay, well, if we're going to do that, then we really need to have some type of genetic counselors at the table. Thus, we entered into a partnership with Color Genomics. And so we now have genetic counselors that are right now handling, they're not getting requests from 100,000 individuals, but they are definitely getting a decent number of requests for what does this mean? The answer isn't always certain. So this is still an exploration and process. So that's one thing that you have to recognize. And this is one of the things I try to do within my own program and tell my own students that at the end of the day, you can't just say that data is data, especially if you're pulling it from humans. And so I was telling some people about this last night, that a lot of the computer scientists and the data scientists that are in the informatics program, I send them out to shadow out in the hospitals. And they have to do this. Otherwise, it's like, so for instance, Yo Chen, when he was a postdoc and he was starting to get involved in like looking at trauma data, I was like, you need to go spend some time in trauma. And he came back to me after about a week and he said, I hope I never see a gunshot wound again. So it's like, but he had a much better understanding of how the physicians interacted with the patients and how they were doing documentation. The second question, which is about wrangling and about how do you do data curation, I don't have a good answer for this. It's not sexy. It's not fun. Nobody likes to do data curation. The only thing that I can recommend at the moment is that you do it once and you only do it once. This was a big problem for us. I'll give you another example of where we were able to address this. When we were making our de-identified medical records data accessible for research, we created unique IDs for every record for every research study. What we learned was that the investigators were getting their postdocs and students to do data cleaning, and we were not asking them to redeposit that back into our environment. And so they would say, okay, well, I'm going to do a study on like T2D, and now I'm going to go do a study on hypertension. And they're going to issue their query, and they're going to see records on the same patient population. And they're going to go, I just annotated and curated, 100,000 of these records. Why can't I not link these two environments? And so that led to a change in policy where we said, okay, you know what? Unique IDs, it's static, it's for the same investigator, but it's also for everybody within the institution. And that was just like a really simple tweak that allowed us to do redepositing of all of the annotation that was done. And so it's a process that kind of drives things moving forward. But the process itself is not fun. It never will be fun, right? Data cleaning is just something that, like, with all of us, it took us almost 2 years to, we have an entire quality and cleaning core that Robert Carroll and Chunhua Wang up at Columbia run. And I don't want to be them, but they do a great job of it.
That looks at automated means of pipeline development and so on. Can the data curation task be accommodated by such a pipeline?
That's a seeded question. We talked a lot. So what Brian's alluding to is so Dan Atkins chaired this National Academies Committee that we just published the report on for automated workflows in the future of biomedical science research or scientific research. And one of the things that we do talk about in that report is the need to have better data curation strategies and have that embedded in the system. But we also, in that report, if you get a chance to look at it, we talk a lot about human in the loop with AI-driven workflows, and that you're always going to need the human to be there, but you want to make it easier for the human to interact with the system. So you don't want to have curation, like for instance, you don't want curation to be done outside of the environment and then have errors occur when you bring the data back in. You want to have the entire curation process as one part of the pipeline. We haven't solved how to do this yet. That's kind of next generation automated workflow. That's what we talk about. Oh, sure.
It's up to you, however you want to do it. I can't see it on the screen. All right, so I'll go ahead and ask Vinod's question. So Vinod Vidiswaran asked the question of, thanks for a great presentation, Brad. On the research infrastructure, de-identification, say, different use cases may need different versions of data. When building an infrastructural resource like the DID data set, how do you design ahead or build variations as you went along?
Oh, okay. Great question. So does everybody understand that question? Short version of the question, I'm gonna rephrase what Vinod said, is that, so let's say that you need to have different versions of the data to solve different problems. Let's say that you need one data set that's highly specific in geographic detail, and you need another data set that's highly specific in like date of birth. For instance, you're studying neonates. Can you have two different versions of the same underlying data set? The answer is yes, but there's both a computational solution to determine whether or not the two data sets could be used to triangulate against the underlying data. And then at the same time, the way that we've done it is we don't test for triangulation, but you could, which the Census Bureau does when they share lots of data. We ended up just putting it all into policy and procedure, in that this is just a matter of making sure that there's separation of those data sets when we've created different versions of the underlying population. That's the short version of that answer. Yeah. You want me to read it? All right. Really interesting talk. Thank you. No, they said thank you. Lots to chew on, and related to your points about students going into the hospital. But with current future public access to the resources you've generated, what do you find to be the most exciting and most concerning, e.g. unintentional negative impact kinds of applications from these data? That's easy. Okay, so I have problems sleeping. Because I've been running privacy and security for all of us for about 2 years now. And for anybody who's ever managed very sensitive information resource, what I'm worried about is somebody who was like me as a graduate student. I know that sounds weird, but I was that type of guy who wanted to just poke holes in the system and show how you re-identify people. And I can tell you that the data is it's not easy to re-identify people. We never say it's impossible though. What I worry about is that there's going to be somebody who enters into a use agreement with us and then just completely ignores the use agreement and does one of two things. Either they snarf all of our data and they throw it up onto a publicly accessible environment that we no longer have any control over, or they actually do a re-identification and say to hell with your use agreement, people are being put in risk and I need to demonstrate this to the world. That keeps me up at night. I worry about our program showing up on the front page of the New York Times in a very negative way. So that's one of the greatest concerns. the other question about, what is the most exciting, the most exciting in my opinion is that what's going to be happening with Bridge to AI over the next couple of years is that you're going to see an investment in by the NIH to create 6 very large data sets that are going to ensure that we have diversity and representation at the table in a manner that we haven't seen this for these types of data sets historically. So that's like a really great opportunity. It's going to evolve over the next couple of years though.
So in response to Arvin's question and your response, what do you do with sort of repetitive tasks that people don't love to do? There was a quite compelling PBS NewsHour segment a few weeks ago about hiring, intentional hiring of large groups of autistic individuals who were quite competent and quite reliable, supposedly, to do these kinds of tests. Any experience along those lines?
I do not. However, I will give you another illustration of some of the work I've done with Daniel Fabry. So we had a grant from the Office of the Director a couple of years ago to create crowdsourcing systems, specifically for annotation purposes for machine learning. And so we've developed a system, published a couple of papers on it that we've used at Vanderbilt and a couple other sites, where we've hijacked the med students and the physicians and the nurses into helping us do annotation of records. And so we've embedded it into student classes where, we'll give an assignment for annotation for like T2D as an example. And so we created the infrastructure to like bring forward to them de-identified records. And we'll ask them like, does this record have X or Y or Z, or where does it occur in the record? Now, the thing about this is that, as with any annotation, you need to get reliability. And so what we showed was that you really need to get a decent number of people annotating in order to get certainty in the annotations. So we didn't go to autistic individuals, but we did go to people who had slightly better than random knowledge about medical phenomena. It's worked so far for about 10 different projects, but it's still very much in its early stages. I think it has legs, but we do need to figure out how to scale it up, because there's only so many times that you can go back to the well to get people to invest their time. I would say that there have been illustrations of how to do this at scale with the concept of what's called games with a purpose. And so if anybody's interested in this, you should look at the work of Luis von Ahn. Has anybody ever seen CAPTCHAs or reCAPTCHAs? I'm sure you've seen it. So Luis invented CAPTCHAs when he was at Yahoo, but the whole notion of a CAPTCHA or reCAPTCHA was really great, because like it was partnered with the Million Book Program, where in order to get access to something, you force somebody to type out what letters they saw on the screen. So it's like all these old books, very difficult to read. And so you get an answer. The answer isn't always correct, but you get enough people to give you the answer. On average, it's going to be correct. So crowdsourcing may be a way of scaling this up. Don't know exactly how it's going to be done yet.
I don't know how much time we still have. So I'm one of your participants in the study. I'm in it. and I actually, I'm like you early, so I'm going to try to figure out if I'm going to find myself based on rare variants that I have access to from other sources about myself, and see if I'm in the thing. I got blood drawn about 2 months ago, so I think I am in the batch that you are there. Okay. So I do think this re-identification is an issue, but I do also think there isn't very much evidence. I think people worry about it too much. I think even though you are worried about it. I am with George Church that if I put my SNP profile on the internet, not that much bad things will happen. And I mean, I did buy long-term care insurance before I did any genetics. The other question is a more scientific one, and that is about 90% or so of human variation is in Africa, and most variation is in Europe and Asia, and the LD profile in Africa is lower. So if, meaning shorter, so even if we had as many Africans as we had Europeans in all our big GWAS studies, we would not be able to predict as much in those populations. How are you going to go about fixing that part of discrepancy, which is kind of one of the underlying biology?
I'm not going to answer your second question. I don't have an answer to it. I think it's a great opportunity for people to provide feedback and write papers on how to address this. So I'm not going to answer that question. Is that okay? So let me jump on the first question if you don't mind, because that's a big one. For those that know me, like I spend a lot of my time doing research in privacy and identifiability work. So your perspective on privacy is one person's perspective on privacy. And unfortunately, first of all, I agree with you wholeheartedly. I think that the problem of identifiability has been overblown. However, I don't think that this is based on my experience. I don't believe that the re-identification problem is one of a personal privacy issue. I actually think that the reason why we can have problems is that if there are promises that are made by the organizations that are sharing the data, if it is shown that those promises cannot be adhered to, then it ends up providing less faith in the research infrastructure itself. And I worry about what the implications of that, where somebody goes, the NIH gave us this promise and the NIH broke that promise. Will not matter who was re-identified, will not matter how they were re-identified. What will end up happening is that there will be a perpetuation of stories in the media about how horrible of a research sponsor the NIH is, or Vanderbilt is, as being the steward of that data. So if an individual is interested in providing their information into an environment where there's less control, like PGP, like what George has set up, great. That is one opportunity for doing so. But if there's a federal agency that's taking responsibility for that sharing of that information, there's a different situation in hand. So it's not just all about personal preference. This is where things are going to go. I think it's a great discussion.
Matthias Kratzler, NIH funded to do rare disease research in the RDCRNs and other networks. We have formally evaluated that, and it gets back to Margaret's point. It's what your study participants tell you. You ask them, they gave you an answer. So that privacy is not their main concern, participation is, and particularly for minority population. And now, largely white audience tells non-white audience, oh, we know the truth about privacy, and therefore we will exclude you from participating in studies sufficiently. I think the key point is, and we are doing that in the NIDDK KPMP purposefully, that it's not us, it's the participants who are making these policies. And those participants derived policies are featured as such to participants. And we have press releases prepared if we show up on the New York Times, where our participants will respond to these communications. And so be very careful that we don't perpetuate the same pattern as we have done before. If we say we are listening to study participants, we have to, even if they tell something to us where we feel we would not make that statement.
No, it's a great point. And so as we're definitely not in disagreement, it is really a matter of tailoring the data disclosure policies to the expectations of the participants. There's only one thing I will caveat this with, which is a bit of research from the economics community and the behavioral economics community. So one of the things is that many people are very poor reasoners about risk in the future. And that if you offer them a service right now in exchange for information or exchange for an acknowledgement that they will accept risks in the future, most people go, I'll accept that service. I'll become a part of your project, or I will, you know, click through the end user licensing agreement on your website and just give you all the information that you want about me. And then when there's actually something that happens in the future, people have a very vitriolic reaction, and they go, oh, well, if only I had like known what exactly those risks were. So like, well, no, we explained that to you at the beginning. And so that puts you in a very strange situation, because you're then saying we took your perspective and we opened up the system. Sometimes it's better initially to have a bit more protection and then slowly open it up over time once we have a better understanding of how the system's going to play out. I think this is a learning process. I think that we're in the midst of changing our traditional views of what research infrastructure and what cohort studies look like, but it's going to take time. Again, we're in agreement.